1927, the Carquinez Strait, separating the rapidly growing San Francisco Bay Area from the Sacramento Valley, was spanned by a single three-lane bridge, which carried traffic in both directions. Hand in hand with the development of the automobile, more and better roads were built, and California was a leader. The Carquinez Bridge became a classic bottleneck that 10 million vehicles were trying to squeeze through annually. But solving traffic problems was nothing new to California. Crossing at Carquinez became the major concern of the Bridge Department of the Division of Highways of the Department of Public Works. They tackled the problem right after World War II. Several possible solutions were proposed. For example, the widening of the existing bridge. By 1947, they had decided on a new bridge, paralleling the old one, to be erected approximately 200 feet upstream. For navigational and aesthetic reasons, it was to be as much like the existing bridge as possible. A preliminary design was made. The detailed design was revolutionary in the bridge business. This was to be the first major bridge in which all members were to be shop welded. But why was this to be a welded bridge? There were two reasons. First, there would be less steel required, 15% less. Second, maintenance would be easier, hence less costly. To appreciate this, let's look at the details of the old bridge. The individual members of the towers and trusses are composed of two built-up longitudinal segments connected by plates, lacing, and hundreds of thousands of shop rivets. All of these detailed parts and rivets present surfaces particularly vulnerable to the severe atmospheric corrosion conditions of the Carquinez Strait. Welding would eliminate most of the vulnerable areas. Welding would provide smoother surfaces, easier to paint, with a resulting uniform and long-lasting coating. But the proposed bridge did not materialize because of financing delays. Still, a new threshold of engineering had been crossed. For the first time, welded construction had been applied to the design of a major cantilever-type bridge, and the design was practical enough to receive serious consideration. Although the Carquinez project was delayed, major strides in welded design on smaller structures were being made by the Bridge Department of the Division of Highways. Beginning in 1952, welded girder bridges started going up all over the state. Some of these boasted spans of over 200 feet. Also during this time, United States Steel Research completed the development of a remarkable new constructional alloy steel, USS T1, aimed principally at applications in other fields. To prove its strength, weldability, and toughness under unusual stress, full-sized pressure vessels were tested to destruction by internal pressure and terrific impact in a dramatic public demonstration. These tests aroused the interest of the California bridge engineers. T1's remarkable properties and its weldability could affect substantial weight savings and design simplifications if used for the most heavily stressed members of the bridge. Let's look at some of the design factors. In designing a bridge, individual members are analyzed to determine the stresses that are imposed by the structure and by the live loads to be carried. Such a member is finally proportioned to resist these stresses in combination with those from other forces which affect the structure. This highly stressed lower chord member, for example, will carry a compressive load of approximately 4.5 million pounds, 4,610 kips to be exact. Use of A242 type steel at an allowable stress in compression of 17,620 pounds per square inch would require a reinforced box section with two plates 36 by 2½ inches, two perforated plates 26 by 1 1/8 inches, and one plate 21 1/2 by 2 1/2 inches, weighing 955 pounds per foot, or 53,000 pounds for the member. But by using USS T1 steel at an allowable stress of practically twice as much, 34,340 pounds per square inch, and with a lower loading due to the reduced weight of other members, thicknesses of plates become 1 1/4, 3/4, and 1 inch. This USS T1 member weighs only 27,000 pounds, only 487 pounds per foot, representing savings of 468 pounds per foot. A total weight savings of 26,000 pounds for a single member. Such savings offered highly attractive design advantages for T1 steel. In the suspended spans, lighter T1 members would minimize stresses to be carried by the major tension and compression members in the tower areas. And, just as important, T1 used in the highly stressed tower members would provide the highest strength to size ratio, greatly reducing the massiveness of the members. Before deciding to adopt T1 steel for the design and to completely satisfy themselves, the California Division of Highways initiated their own series of tests on USS T1 steel. Tests were made on steel plate and on butt-welded joints to confirm the strength, ductility, and resistance to fatigue. Results were well within the specification requirements. An average yield strength of 111,000 psi and an ultimate strength of 120,000 psi. And calculations showed that a joint efficiency of 100% of base metal strength could be obtained. Since these and other tests proved the reliability of this new steel, the bridge was completely redesigned to incorporate USS T1 in place of some of the weldable structural steels in the first design. In the final design, 6,440 tons of A7 type structural steel were selected for lightly stressed members. For more highly stressed members, A242 type steel proved most economical. These members were fabricated of 5,370 tons of USS Tri-10 steel, a weldable, high-strength, low-alloy steel already used in many major bridges in the United States. And 2,910 tons of T1 were designed into the bridge's most heavily stressed members. The steel to use for an individual member was determined generally on the basis of limiting the maximum plate thickness to 1 1/2 inches. Welding plates thicker than this was considered uneconomical. For example, if the plates of the member designed of A7 steel exceeded 1 1/2 inches in thickness, the member was designed in USS Tri-10. If this still did not reduce the plate thicknesses below 1 1/2 inches, it was then designed in USS T1 steel. And welded construction offered another advantage. The number of basic structural sections was reduced to 3. H sections for tension members, box sections for average compression members, and reinforced box sections with a central web plate for the heaviest compression members. In addition to reducing the number of sections, other important improvements were possible. For example, in one of the large bottom chord members of the original bridge, there were 14 principal components and more than 1,000 stitch rivets requiring over 3,600 punched and reamed holes. In the same member of the new bridge, there are 5 principal components, and all rivets are replaced by 340 feet of 3/8 inch automatic fillet welds. And another advantage of welded construction: plates could be spliced together with butt welds to achieve the exceptional length required for the larger members. 100% efficiency welds also made it possible to weld thicker plates on the ends of members, thus compensating for the loss in section due to holes for the end connections. This novel use of butt welding was specified in the design by the California Division of Highways because of the 20% weight savings which it made possible in tension members. By the time the new design was finished, traffic problems justified start of the entire project. Competitive bids were requested. The contract for the superstructure of the bridge was awarded the same organization which built the original Carquinez Strait Bridge over 30 years ago, American Bridge Division of United States Steel. Even for the organization that has built so many of the world's greatest bridges, shop welding all of the individual members of a major bridge was a real challenge. It took many kinds of welding, fully automatic and semi-automatic submerged arc and manual shielded metal arc welding to do the job. Automatic submerged arc welding was extensively used in the buildup of the members after the edges had been prepared to obtain a tight and accurate fit. These 3/8-inch fillet welds running the entire length of the sections were made at speeds in excess of 12 inches per minute with single electrode and 20 inches per minute with twin arc. On heavier sections, up to 38 passes were required to complete a single weld, as on this giant member, one of the 4 principal tower posts, the largest members in the bridge. Submerged arc welding produces smooth, uniform welds and minimizes warpage problems. Mild steel rods were used for submerged arc welding, the A7 and A242 steel. A rod producing higher strength weld metal was used for the T1 steel. Butt welding was done with electrodes which produced welds having physical properties comparable to the base metal. Radiography assured the soundness of all butt welds. Face cuts were taken on ends of completely fabricated members to assure close fit in final assembly. After fabrication at American bridge plants at Ambridge, Pennsylvania and Gary, Indiana, the individual members were pre-assembled. By reaming the bolt holes through each member and its connecting plates while the members were assembled, perfect match was assured in the final erection. Assemblies were then knocked down and members shipped to a storage area at Richmond, California. All members of the superstructure were blast cleaned either in the shop or the storage area to remove mill scale and provide a good surface for painting. Then each received several of the ultimate 6 coats of paint. Some members, of the painting crew that is, received more than 6 coats. But a good paint job is a good investment, according to California highway officials. From the storage area, members were barged 30 miles up the bay to the bridge site. Because of the reduced weight of members, shipping and barging costs were also reduced. This is what might be called a stacked deck, stacked to make the job of erecting the bridge easier. All members have been put on the barge so that they will go into the superstructure without any shuffling. Derricks operating from barges were used to set the first members in place. But it is men with a love for bridge building who are the essential ingredient in the construction process. Every job is important. A little more slack in the line here. Hold back there. Up a little with the hoist. Keep your eyes open. Huge members, carefully balanced to go into place at the right angle, are gently lowered to match up with connecting plates. Connectors stand ready to put in drift pins and bolts as the holes line up. The California Division of Highways specified that all field connections in the superstructure would be with high-strength bolts, all tightened to a predetermined tension. tightening was done with power-driven impact wrenches and checked with Paul Bunyan-sized torque wrenches. The use of high-strength bolts produces superior joints because they transfer stress by friction developed between the plates. And while all this activity was going on up here, down below, the vital traffic through the strait continued without a minute's delay. All of this climbing up and down points up one of the new problems in erecting this unique bridge. The smooth, clean members, without rivet heads or lacing bars, did not offer a toehold for the iron workers in moving around the structure. In spite of this, the construction superintendent, a veteran of many major bridges, says that the Carquinez Strait Bridge went up more easily than any in his experience. A false work truss, used as a temporary support during construction, was later disassembled, and its members became part of the suspended span. Derrick travelers operated on the structure itself. Member by member, the bridge men placed ton after ton of steel into the pattern established by the bridge designers. From the center pier and each of the other two main piers, the steel arms of the cantilever and suspended spans stretched farther and farther towards each other. The traditional completion symbol of American bridgemen, Old Glory, waves proudly from the member used to close the span. Still working with infinite care, the bridgemen ease the closing member into place. Once again, the Carquinez Strait had been spanned. Of course, painting and paving operations must be completed before traffic can actually flow. Compared today, the old and the new bridges provide a vivid picture of the advances made in 30 years of bridge design. A comparison of continuing progress in steel research, in new welding techniques, and in new uses of bolts. The Carquinez Bridge is an ideal combination of the three strength levels of weldable structural steels. At the extremely high strength level, the California Division of Highways says that the use of USS T1 trimmed 2,128 tons of steel from the structure, reflecting a substantial dollar savings. At the intermediate strength level, the choice was USS Tri-10, a high-strength, low-alloy steel. And at the lower strength level, the job was rounded out by the use of A7 type structural steel. The correct application of each steel resulted in other savings. Foundation costs were lowered because of lighter weight of the structure itself. Shipping costs were lowered because of lighter weight members. and erecting was made easier by the lighter, simpler members and bolted joints. And the clean, smooth, welded members of the new bridge will minimize annual maintenance costs. The new Carquinez Straight Bridge stands as a tribute to welded bridge pioneering by the California Division of Highways to United States Steel's American Bridge Division, which completed this revolutionary bridge ahead of the contract schedule, and to the research and production of United States Steel, the single source for all the steels required. The bottleneck across the Carquinez Strait has been broken. A new era of opportunity has been opened to bridge designers.